Now at the equivalence point, we already have all of the vanadium having reacted with all of the tin 4 that has been added to produce our two products, the vanadium 3 and the tin 2. So let's rewrite that equation over here. So 2 vanadium 2 ion plus the tin 4 has reacted to produce 2 of the vanadium 3 and also our tin 2 ion. So initially, after adding all of the 50 ml of our tin 4, what we're able to have is completely zero for the vanadium 2 and the tin 4 ion. And so all of the vanadium has been converted into vanadium 3. Likewise, all of the tin 4, which was 2.5 millimoles being added, all of it has been converted into our tin 2. Let's divide now these number of moles by the total volume. So initially, for this one, we have 50 ml of vanadium 2 plus 50 ml of our tin 4 added at equivalence. Same here also for the tin 2. Just so we can get the concentration of the vanadium 3 and the tin 2 ions. Now at the equivalence point, we expect that a very small amount of our vanadium 3 and our tin 2 will reconstitute or reform our original ions, the vanadium 2 and the tin 4, so that we have a certain amount, negative 2x, changing from the concentration of the vanadium 3. And for the tin 2, a certain concentration, x, will be converted into their corresponding ions, like so. So that at equivalence, we're able to get the following. So let me just simplify. That's 5 millimoles divided by 50 plus 50 ml. That concentration is 0.05 minus 2x. And for the tin 2, that will be 2.5 divided by 50 plus 50. That's 0.025 minus x. Now with our ICE table complete, we can now make use of our KEQ value. So we now write our equilibrium constant expression. KEQ, basing on our overall redox reaction, should be equal to the concentration of vanadium 3 squared times the concentration of tin 2 divided by the molar concentration of vanadium 2 squared times the concentration of tin 4. Now plugging in the values, we now get the following. KEQ is computed in the previous video. That's 6.84 times 10 to the power of 13 equal now to the concentration of vanadium-3 in molars. That's 0.05 minus 2x squared times the molar concentration of tin-2. That's 0.025 minus x divided by the concentration of vanadium-2, 2x quantity squared, times the concentration of tin-4 as well. Now plugging all of this into our calculator, we now get the following. So we have 6.84 times 10 to the power of 13 equal now to 0.05 rather, minus 2x squared times 0.025 minus x all over 2x squared times x. So what I like to do is, just so my calculator doesn't hang, I just cross multiply this in my mind. So I put this one on the other side because I find that my calculator works faster if there are no denominators like here when I do my shift solve. So let me just plug all of these in now. We have 2x squared times x, that should be 4x cubed equal to 0.05 minus 2x squared times 0.025 minus x. That's what I like to do, but I don't think there really should be much of a problem in there if you just input all of this as it is in your calculator. It's just that it probably would take a bit longer for your calculator to process. So what I like to do is I really like to cross multiply the denominator to the other side. So using our very useful shift solve function in our calculator, we should be able to get the value of x. So let's just wait for a bit while our calculator processes it. Okay. The value I got from my calculator is 0.056. So I find that one hard to believe because if you can see here, the concentration is 0.025 initially for our tin-2. So how could it go from a very low concentration of 0.025, you subtract it with 0.56. That should give you a negative value, which is not acceptable. So we won't accept that one. Let's try to redo that one again. Point 0.025 minus 2x quantity squared times 0.025 minus x divide by 2x quantity squared times x. Okay, so that's a more believable value that my calculator has given me. X is now equal to 6.11 times 10 to the negative 7 molar. So how can I assess if the value given to me by the calculator is believable or not? Obviously, you cannot have negative concentrations. The value I got earlier, 0.56 molar, will give you 0.025 minus 0.56 equal to negative 0.535. And there is just no negative concentration at all. Furthermore, if you look at our value of KEQ, it's rather large. So what we expect to see is that our X must be a rather small value. So it should be quite small. 6.11 times 10 to the negative 7 is something that I would expect to appear in my calculator. And so with that already computed, we now know that the concentration of our vanadium 2 at equilibrium is 2x. Or that is now 2 times 6.11 times 10 to the negative 7, 1.22 times 10 to the negative 6. And for vanadium 3, since the value of x is so very small, basically what you have in here is 0.05 minus 2x. It's basically just almost equal to 0.05 molar still. So it's like nothing has changed at all for the concentration of vanadium, since a very, very small amount of it has been converted into vanadium 2. Now with these molar concentrations already known, once again, we compute the value of our E. So E here is going to be computed just the same as what we've done in our previous video. So we have negative 0.255 minus 8.314 times 298 all over 1 times 96, 96,485. Ln, the concentration of, from our overall redox reaction, vanadium 3 should be on the numerator. That's 0.05 divided by the concentration of vanadium 2. Looking at the overall redox reaction, that should be 1.22 times 10 to the negative 6 on the denominator. So plugging all of this into our calculator, we now get our value for the cell potential at equivalence point. So you have 0.05 divided by 1.22 times 10 to the negative 6. So that's equal to 0.018. Not molar. That's volts.